welcome to Podcast.init, the podcast about Python and the people who make it great. I would like to thank everyone who supports us on Patreon. Your contributions help to make the show sustainable. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at www.podcastinit.com/Linode and get a $20 credit to try out their fast and reliable Linux virtual servers for running your app or experimenting with something that you hear about on the show. You can visit the site at www.podcastinit.com to subscribe to the show, sign up for the newsletter, read the show notes, and get in touch. To help other people find the show, please leave a review on iTunes or Google Play Music, tell your friends and coworkers, and share it on social media. Your host as usual is Tobias Macey, and today I'm interviewing Glyph about Automat, a library that provides self-service, finite-state machines for the programmer on the go. So, Glyph, could you please introduce yourself?
Sure, I'm Glyph. I've been doing Python for quite a long time. I am usually interviewed in my capacity as the founder of the Twisted project, so it's refreshing to be here today to talk about another one of my projects, because I do have a few. I'm an open source maintainer and a professional programmer for the last closing in on 2 decades now, and you can see lots of my public speaking at PyCon and other conferences around the internet, so I'm what passes for a public intellectual, I guess, in our industry.
Yeah, it's funny. This is actually the second time that you've been on the show, and in neither case have you been talking about Twisted.
It's you've got good taste, I guess.
I figure it's just a subject that's probably been pretty well covered elsewhere, so we can discuss other things. So for anybody who missed it, you were on fairly early in this series. Don't remember the exact episode number, but I'll put it in the show notes. But you were talking about the idea of ethics in software development. So I'll refer people back to that episode if they want to learn more about that topic. But in the meantime, how did you first get introduced to Python?
Well, hopefully this story changes every time. It's interesting for folks who might have heard it before, I'm hoping they're all listening wrapped to each episode of your show. But I was introduced to Python because I was working on a video game in Java, and as games tend to be, it was very script heavy, lots of things that needed to have dynamic behavior, and for a variety of reasons, I wanted to try and rewrite it in something new, and because most of the logic in Java was hash table lookups of dynamic classes, after learning about Python's dynamic method lookups and semantics and runtime metaprogramming, like 90% of the code just dissolved. It did nothing because it's trivial to write an app in Python that needs to have dynamic behavior and get things wired together into hash tables of arbitrary methods, because that's kind of what the runtime is already. So that was a great introduction in about, I want to say, 2000 to Python 1.5.2, still the best version of Python ever, I'm sure. And so I've been doing it ever since.
As I mentioned in the introduction, we were going to talk about your Automat library. And to begin with, I'm wondering if you can just do a quick high-level overview of what a state machine is and some of the cases that you might want to use one.
So that's an interesting question, because all computers are state machines, and so you kind of might want to use a state machine anytime you want to use a computer. But of course, that's way too broad of an answer, especially when it comes to dealing with a state machine library. So the real question is, what's a finite-state automaton, or what are certain formalisms around state machines that are interesting? And the interesting thing about modeling state as a finite state automaton or a deterministic finite state machine is they're good for modeling objects that change over time, that have different behavior depending on what has happened to them previously. So it's very easy to accidentally implement yourself something that is effectively a deterministic finite state automaton by setting a bunch of attributes and just checking them before certain methods do things. But of course, that's very difficult to assert anything interesting about, or to visualize, or to understand. And so really, it's the idea behind a state machine library is that you might want to use a formal state machine to be able to get more insight into and be able to more rigorously analyze the code that you're already writing that already has this behavior that changes over time. So these different sort of types of state machines, deterministic finite state automata, are objects that have a state and that have transitions between different states, inputs that can cause them to potentially change states, and outputs that are things that happen as a result of them changing states. So there's the usual place that state machines are applied is in parsers, because there are an explosively huge number of states that something that could, for example, parse C or Python, they might have millions of internal states. And so there are parser generators like Yak and Bison and Flex that do a bunch of the machinery associated with manipulating state machines, so that you don't have to know that there's a state machine under the covers. The kind of state machine that Automat is actually for kind of a higher level application. It's for something where you've got an object, you know that it's changing over time, you want to know that it's there, you kind of want to know what state it's in. So it's almost the opposite use case of what the usual kind of academic literature about state machines is about.
And there are a number of other libraries on the Python package index that show up if you do a search for state machines. So what is it about the offerings that were available, or the lack of offering, that made you feel the need to build a new option? And what are some of the ways that it differs from what was already available?
Well, no disrespect to any of the authors of any of those libraries, but none of them were terribly mature. Like, none of them struck me as particularly like the thing to compete with. If I was going to write a web framework these days, I would have to have a big section on my website about how does it compare to Django, and how does it compare to Pyramid, and how does it compare to Rails, because they're kind of a couple of big names that people are going to know about that do this thing in a particular way. And when I looked around on PyPI, because I did, before I started this project, I did kind of a more thorough analysis of the field of competitors than I usually do before starting an open source project, because it's kind of an academic computer sciencey thing, and I'm not a particularly academic computer scientist, so I wanted to see if somebody else had already done this. And what I found was that they were all sort of just enough to solve the problem that their author had, and they all so that was the initial problem, was that none of them were really kind of advanced enough to be worth contributing to or extending, as opposed to doing my own thing. And the big difference is that not only were they not super featureful, but they also all kind of fell into the same trap, which is that they provided convenience functionality. And one of the ways that Automat is really different is that, while I certainly hope it's convenient to use, it doesn't provide anything that goes outside the scope of the specific type of state machine that it is. I believe the correct terminology for what it implements is it is a pure mealy machine. This is as opposed to other types of state machines like Moore machines. And the thing that I really want, the reason that that was an important and interesting thing for it not to provide convenience functionality, is much of the convenience functionality in these other libraries are things like a hook every time you enter a state, or a hook every time you exit a state, or interaction with other pieces of logic associated with the state machine that would help you sort of debug it or diagnose issues with it, that were about stepping through the code around the state machine and about allowing you access to its internal state, so that you could say, like, what's the current state and what are the transitions away from this state? And the problem with that is that the goal of having a library to reflect this type of state machine, in my mind, is to provide consistency of behavior. Because if you have an object that might be in a number of different states, what you want, the reason you want a library to help you organize that object, is the caller of that object should just say, like, I want to send a message. And if you have a message sender that can be in 17 different states, the caller shouldn't have to care that it's in the connecting state or the connected state or the timing out state. It should always do the same thing as far as the caller is concerned when you say send a message. And the problem with exposing the current state of the state machine, for example, is it seems helpful. Like, you might want to know that while you're debugging. You might want to instrument it a little bit. You might have logic that was like a little different depending on what state it's in. But the problem is that that pushes the behavior, which, in order to get the benefit of a state machine, which is having this consistent interface for outside callers to know that they can just send it the same message and it'll do the appropriate thing for its internal state. Instead, now there's always this opportunity that the state machine can say, well, you really can only call this and these two states, so always check before you call. And all of the utility that you get from knowing that it's a state machine and having all of these pieces of information about it, like the transition table, goes right out the window, because now the actual behavior is being decided by this combination of the innards of the state machine itself and whatever the caller is doing to check before it provides the inputs. So the idea behind Automat was to make everything very, very opinionated, I guess is the popular term for this these days, and to force all of the logic that should be in an output of the state machine to be in an output, and to force all of the inputs not advertise anything about the internal state of the state machine unless they explicitly want to.
Yeah, I can definitely see where being able to expose the internals of the state machine would very quickly lead to a leaky abstraction and cause people to take shortcuts and then, like you said, thereby sort of short circuit the capabilities that you're asking for in the state machine in the first place. And at that point, you might as well just go back to your nested conditionals and just not even bother with trying to incorporate the state machine library.
Exactly.
One of the other questions I have too is you were mentioning how you were evaluating the other libraries that were available on PyPI, but what is it that first drove you to even considering either contributing to or creating your own library for state machines? What was the specific need that put you in that situation?
Well, as it turns out, we are here today to talk about Twisted, because in fact, the thing that led to the need for state machine library was really the hundreds of really unfortunate informal state machines that live inside Twisted. In particular, the thing that motivated me to really create this as a library was Ashwini Oraganti was developing a new TLS library at one of the PyCon sprints, I believe 2 or 3 years ago. And she was looking for a way to represent the TLS state machine and looking around for examples in Twisted that were kind of good examples. And unfortunately, there are very few. And the few that there are mirror that exact same criticism that I have of state machine libraries that others have written, which is that abstractions in Twisted, which attempt to model things as state machines, expose lots of internal implementation details. They have a state variable. It's very easy to tell what state they're in. It's very easy to add little hooks to different elements of the state transition machinery. So I wanted to say, like, here's a way that Twisted does this well. And there are lots of things in Twisted that really kind of need state machines and don't have them yet. So one in particular, the first that I believe is already in a Twisted release, because Twisted does depend upon Automat now, is client service. So in Twisted, you got this notion of an outbound connection needs to stay up because it's a pipe that you're streaming data to some other service, and it's a pipe that needs to be maintained consistently, and if the connection goes down, it needs to come back up. And our original implementation of this, reconnecting client factory, is kind of a legacy API for a whole bunch of different reasons. It doesn't work super well with SSL. It uses older interfaces in the internals of the reactor. There's a lot of tight coupling. So we knew that we needed a new thing that could do this job in a more flexible way. And one of the interesting things about this is it turns out there's actually a bunch of states associated with reconnecting, because there's the initial state where you start off and nothing has started. Then the application can say, okay, start up and start maintaining the connection. And then it's in the connecting state. Then the connection actually gets established, and it's in the connected state, and later the connection might be dropped, or you might shut it down, which are both different ways to reach other states, like the disconnected state or the reconnecting state. And this seems very straightforward, because if you think about it from the perspective of, like, how do I implement this in terms of some logic inside the methods, you start thinking, oh, well, I'll have like a flag, and the flag will say, am I connected or not? And if I'm not connected, then maybe I should start connecting. And if somebody tries to send a message over this channel and it's not connected, maybe I should buffer it or something. And so, like, you start adding all these little if checks. But the problem with all those little if checks is that with one flag, you have two cases to worry about in every method. So you take all your methods and you multiply the work by 2. And sometimes the work of that other branch of the false case is actually the same, and you can look at the method and say, oh, well, this method, it doesn't matter. It behaves the same way either way. That's when you got one Boolean. Then you get 2 Booleans. And now you have to add 4 cases to every method. Then you get 3 Booleans and it's 8. And pretty soon you're into a combinatorial explosion that you can't manage anymore. And the interesting thing about this is not only do you have this combinatorial explosion, but because it's a state space explosion and not an actual code complexity explosion, like you've got these flags, and until you remember to go in and add all the if checks that you need, it doesn't look any more complex. All of the bugs can't be caught by code coverage testing. There's no obvious unit test that you need to write because all of your code's covered and you added every case that you could think of. There's no tooling that can help you see the complexity that's arisen. So we rewrote client service to use Automat, and we actually found a bunch of bugs, which we didn't even realize were there. So there's things like that. There's the hostname endpoint, which is the thing that just when you say, I want to connect to google.com on port 443, the amount of state transitions involved in that are kind of staggering. There's a branch in progress right now to rewrite that particular twisted class in terms of an explicit state machine using Automat. And that effort has, although it hasn't landed yet as a patch in a release, it has found a couple of bugs in the way that we do hostname resolution and a couple of edge cases that we haven't handled 100% correctly. Because when you're making an outgoing connection, you think of it as just like, I'm not connected, now I'm connected, there's only 2 states. What could be simpler? But in fact, you have to do DNS resolution. DNS resolution could give you back multiple results. So you start off in the I haven't resolved the host name state, then you're in the I have resolved the host name state. Then you've got a bunch of host names, and then you're connecting to the first one, and you're timing out on the second one, and so that's a discrete state. And then you get all the way to the end of that list, and then you start transitioning into the, oh, now I'm draining the queue of outstanding connections. I don't have any more connections. You got timed calls flying around all over the place here. So this type of logic is very common in an event-driven context, not because it's particularly more necessary in an async program as an asynchronous one, but it's more obvious because you tend to have more objects that represent like connections and stuff, as opposed to with threads, you might have a lot of implicit connections or sub-processes, but you don't have an object that has all the flags on it. You just have like a call stack where you're in the middle of something somewhere. But if you're doing anything concurrent, you very rapidly start having all these flags and objects floating around that might be in a bunch of different states. So that's kind of the genesis of why Automat was necessary for Twisted and where the idea came from originally.
Yeah, and an additional place that I've seen state machines leveraged too is for capturing business logic, particularly in something like e-commerce, where there are certain states that an order can be in and different transitions. So again, it's something that at face value seems simple, but then you start getting into the special situations of, okay, well, what happens if the payment gets declined after the order has been placed? Or what happens if there is a stock shortage after the order has been completed and now it's ready for shipment except for this one thing? So there are various different states that can happen there, and there are certain business needs. But again, as soon as you have multiple different representations of state, how do you ensure that you never get into an impossible state within your program? Because then it's somebody has to go in and manually try to figure out what happened and then resolve it within the situation of the data, which can get quite messy quite fast. And from what you were describing earlier of starting off with the very simple case and then adding a conditional and then just adding another conditional, after a certain point it becomes very tempting to just keep going down that chain because you've already gotten started. So what are some of the signs that people should be watching out for to signify that they should stop adding new conditional blocks and start looking into actually incorporating a state machine into their code?
Yeah, so I think that there's nothing wrong with conditionals. If is a venerable keyword in the structured programming pantheon. But the point where you probably need a state machine is when you have a class and it has a bunch of attributes. You really know you've fallen onto the spikes already when you start adding your 5th or 6th Boolean flag, like is order declined, is order delayed, is, if you have like 9 of those, you definitely want to have a state machine because you got there as a workflow. And to your point, by the way, about like order systems and dealing with different states that inventory and fulfillment and things like that can be in, that is absolutely another use case related to asynchronous event-driven programming. Because what you've got in those types of systems where you have orders coming in and fulfillment's happening and billing, those are all events that are happening to your business. And they might be happening as like a blocking WSGI thread, and you're technical implementation of them, but they are nevertheless, an event has occurred in the world that has now affected your business, and it is touching a piece of mutable state that has persisted over the life cycle of this process that's happening. So the number one sign that you need a state machine right now is you have 6 flags on your object and you're adding the 7th. But the more subtle signs are just that you have objects that are sometimes missing attributes that certain methods need, for example. If you ever see a traceback that's like an attribute error and you say, oh yeah, I just need to check for that first because it's fine that it doesn't have that attribute. Sometimes that's not set yet at this point in its life cycle, but I'll just add another check. Even if you don't have a whole bunch of Boolean flags, a bunch of has-adder checks are another indication that there's something going on there that really needs a state machine.
And for somebody who is at the point where they decide that they're going to start incorporating a state machine into their code base, what does the process look like for adding Automat, and what are some of the steps that they should be considering in the process of adding that to as a dependency to their code base?
Hopefully, the answer to that question is that it's very easy. Automat was designed specifically to be something that's easy to integrate to an existing code base, that's really easy to adopt incrementally. One of the things about the other state machine libraries on PyPI that I didn't mention is they all require that you call some method like input or feed or data or something, some method to tell the state machine to turn a crank on itself. There's a state machine object with its own API. With Automat, the best way you can adopt it is to find some object where you're falling into that 7 flags trap and decide what that object's public interface is. You've probably got some unit tests already. Rip out the implementation of that, replace it with an Automat-based implementation, and nothing about it should change. The callers should all just invoke the methods, which are in Automat's terminology, the inputs, and it should sort of magically work, because the whole goal of Automat is to present this interface that looks just like a regular Python object. All of the state machine wizardry, all of the stuff that's happening with state transitions and state enforcements and whatever, that's all happening inside the object. The outer interface is just, here are the methods, they have return values. And one of the things about that strategy of adopting it is that it kind of forces you to think about, like, what is your real public interface? Quite often when you're designing with Automat, you can remove a whole ton of private flags, you can remove a whole ton of other internal details, but you really need to think about, like, what are the things that are happening to this object over time? Like, how does its state change? The one gotcha that I would say right now about adopting Automat is that there is one extremely subtle detail, which is a known bug, and we are working on fixing it. There's been some implementation prototypes of how to fix this, but you can't produce an input from an output. So if your state machine receives an input and then runs an output method on itself as a result of generating that input, and then that output wants to produce a new input, that recursion will sort of like look like it works, but it actually doesn't. You need to find some way to pop out of that loop and provide the input from the outside. There's a new API coming at some point called Feedback, which will sort of automate the process of doing this. One of the reasons for this is that because an input can produce multiple outputs if the transition specifies it, you can't actually necessarily block on your own input, because Automat tries to provide certain guarantees, and one of them is if you've made your way through the state machine to a particular state, all of the outputs that get you on your way to that state will have run. The idea there is that if some of the outputs set attributes on self, you should be able to rely on those attributes being there. You shouldn't need to have your has-adder checks. You shouldn't need to have do I have my connection yet? It's just in an output that's being generated from a certain state where you should have your connection or your order number or whatever already. You should just be able to rely on it, and you shouldn't have any conditionals at all in any of your outputs. So in order to preserve that property, reentrant inputs are not supported, and probably won't be supported, actually. Like, the thing that's going to make it easier to deal with this problem is that there's going to be better error reporting, and there's going to be a facility for generating what's called feedback, which is like, it'll push the new input into a queue, but you still won't be able to like return the result from that input. You're still going to need to kind of treat that as an asynchronous result that happens later.
And when I was looking at the documentation I was seeing that as far as the actual implementation detail, a large portion of the way that you actually get started is just by setting the machine attribute on the class object or on the class that you're defining. And so I'm assuming that that's using some sort of metaclass hook to be able to then instantiate the internal machinery for the state machine. Is that correct?
Actually, no. There's really very little magical metaprogramming going on in the internals of Automat at all. It will initialize the machine object as a descriptor, but almost all of the magic that happens inside Automat is all of the decorators that are methods of that machine object, like input and state and output. Those set things up so that when you call an input for the first time, it will have all of the state that it needs. So it's actually, for the amount of sort of convenience of the way that you interact with the library and the way that you interface with it, there's actually very little magic going on. And once you understand how decorators work and you understand just like sort of creating a new callable from the existing callable, there's pretty much no other stuff. There's no meta classes, there's no class hooks, there's no inheritance. It's just straightforward, like the decorated method is an object in its own right. It has a documented interface and that's it. And as far as like the internals of the library itself, the way that it's structured in terms of how those methods like initialize their state and interact with the user, those the magical internals are mostly designed around preventing you from accessing any of the internal state of the library. So that machine object is there kind of in the class scope, but once you've defined all of your inputs and outputs and states, it's not really there anymore. You can't really access any attributes on it. It's not an attribute of your instances as far as you can see. You just get attribute errors if you try to reach inside the machine to like grab the state or whatever. So that's really the prevailing design idiom of Automat is everything's an implementation detail. Do not look inside the box.
And for somebody who has different pieces or different workflows that they want to be able to link together, is it possible to compose two different state machines that are using Automat to be able to create sort of a more hybridized or higher level workflow?
Absolutely. Composability of state machines was definitely a goal of the library. And the way that the composability works is that state machine A is an object and state machine B is an object. And state machine A exposes some methods which are inputs, and state machine B exposes some methods which are inputs. State machine A's inputs call output methods that are defined on state machine A, and those can just call methods on B. There's really nothing more to it than that. There is still the rule that A should not recursively generate a new input to A. However, that rule is the same whether B is another state machine or B is just a plain old Python object. So this is actually one of the things that makes adopting Automat kind of so effortless, is that even if every object in your entire code base will eventually turn into an Automat object with a state machine inside it, you can migrate them one at a time, and no two of them will ever know if any of the objects they're talking to are using Automat. It's all just like an internal technical detail. The only thing that sort of leaks out of that right now is the errors that you get when you activate an invalid transition. But invalid transition errors are sort of like assertion errors. If you want to deal with them, you don't actually want to add try, except, catch the invalid transition. You just want to add a definition of that input from whatever state that input's not defined in right now.
And one of the things that I found myself asking while I was reading through the docs is that because of the fact that the implementation of a state machine with Automat is tied to a class, are there any cases where you would want to be able to have some sort of state transition capabilities outside of a class where you're just using bare Python functions, maybe in sort of a scripted environment?
I think the main thing I would have to say about that question is don't be afraid of using little classes. Even if you're in a script, writing a little class to represent your state should be fine. That said, Automat is a very heavily, I guess, object-oriented would probably be the right term, in the sense that the reason you need the class is that you're providing inputs to this state machine, and inputs are really method calls like Python already has, and a syntax for providing an input to a state machine, and it's .word open parenthesis. So I know a lot of people in the scientific Python community or folks who use things like Jupyter often feel like they're not building libraries, they're not building big sophisticated systems, so they don't really use classes as much. But if you have a piece of state which changes over time and it needs to present a uniform interface, it's kind of hard to find a better tool in a class to model that. So Automat could be thought of as like classes plus. And, to those folks who are doing scientific Python who don't think of themselves as like writing technical assets, which like big fancy libraries that need lots of classes, something to remember there, I think, is like list is a class, tuple is a class. Even in Python, int is a class, effectively. So you're using lots of objects already, and there's no reason that you shouldn't define your own as the task befits them. So hopefully in a scripting context, you're not doing a whole lot that involves like long-term persistent state. But if you are dealing with a workflow that can kind of go one of 3 or 4 different ways, an Automat state machine in a little class that's just dedicated to that might be a good way to represent it.
So in the process of building Automat, what are some of the technical hurdles that you've been faced with, and what are some of the ways that you have overcome them?
The interesting thing about Automat as a library is that there's very little in terms of technical meat. Like the algorithms are all extremely simple. It's like loop over this thing, call this thing, set this variable to a new value. So most of the hurdles are sort of more social. One of the tricky parts of it, though, technically is actually the visualization layer. So one of the benefits that Automat can provide to you is if you declare your whole state transition graph declaratively, as Automat makes you do, there's a data structure there that you can then inspect kind of at import time instead of at runtime to say what are all of the states this might ever be in, and then to visualize it. So there's actually a tool that comes with Automat, Automat-visualize. It's like a shell command. You can run it over your Python code and it'll spit out a diagram that shows you what your state machine looks like, and sort of it'll use GraphViz to draw out all of the states and the transitions and the inputs and the outputs. One of the most technically challenging things about writing this library was developing a presentation that made any sense at all, that was readable at all, because there's a lot of data you have to cram into a tiny little space, and it's by necessity it's changing around a lot. Like you add a transition and the entire machine is like a different shape now, and so labels overlap, and it's hard to choose a shape for the way to organize the inputs and the outputs, because if you just kind of let GraphViz lay things out however it wants, the inputs will be like 7 inches away from the outputs that they're paired with because there's a lot of arrows in between them. So we tweaked that a fair amount, and I think we have a reasonably good looking visualization, but that'll probably be where a lot of the kind of like long-term maintenance of the project ends up going, is just trying to make the visualizations look good and trying to add features like not just visualizing it statically where you show what any instance of the state machine might do over its entire lifetime, but to like add a debugger so that you can visualize a particular instance, like what state is it in right now and what transitions did it take to get there, and maybe doing a little animation. So most of the sort of real technical difficulty was either in that part or just in the kind of pre-reading of all of the different Wikipedia pages about state machines, because there's like 90 different kinds of state machine. The differences are very subtle. Luckily, there's only a few that are really of interest in computer science, but there are tons of things that start to touch on like set theory and mathematics and a bunch of other things, which, like I said, I'm not much of a theoretical computer scientist myself, so I wasn't necessarily comfortable with all that stuff, and I had to think really hard about it first, because state machines are almost like cryptography, and that you kind of don't want to have to roll your own theoretical primitives. You want to be building on something that's a little more foundational. So I knew what general shape I wanted for this, and so that term that I used earlier, a mealy machine, was the result of my efforts of scanning through all the different types of finite state machines and deterministic finite state automata and mealy machines and Moore machines, and there were at least 2 or 3 others that I saw, and figuring out where in the hierarchy of different things, which all might be called a state machine, I actually wanted to implement.
Yeah, that was one of the things that kind of stalled me on putting together this particular episode is that state machines as a concept is something that I had been wanting to cover for a little while, but every time I started to try and dip into that space, there are so many different implementations in the Python package index, and then also, as you said, trying to read up on the sort of ideas behind state machines. That's one big rabbit hole to dive into. So when I came across Automat and saw the fairly clean API and low overhead of implementing it, I thought it was definitely a good case study in the ideas of state machines and a practical implementation of it that people could actually walk away with and benefit from at the end of the day. So I was pretty happy when I saw that this library crossed my path.
Well, thank you very much. That is exactly the kind of feedback that I was really hoping for when I first started this library, especially because, there's so many different things you can do with state machines and so many different problem domains that they apply to, that I was really interested in this one specific domain, which is what I think most of the other libraries on PyPI really are also focused on, which is this domain of objects that change state over time, that have kind of like an application meaningful set of some small number, like a couple of dozen at most states, where the transitions are like manually specified. It's not an optimizing compiler. It's not some kind of computer graphics thing. There's no automatic generation of states or lattice reduction steps or whatever to try to like turn something else into a state machine via automation, but to just build your own by hand with some automation. So I hope that by trying to kind of restrict its ambition to this very specific, narrow, vertical niche of what the very, very broad category of state machines are for, it'll be a little more successful than some of the more general entries.
And one of the things that you alluded to briefly is the idea that when you're actually going about testing your code base, when it has a state machine involved, it actually simplifies a lot of the cases because you don't have to worry about the impossible situations that can arise from a business domain perspective. And so I'm wondering if you can just dig a bit into what an actual test case would look like for a state machine versus just the combinatorial conditional explosion that somebody might find themselves in.
So this is actually a very interesting question because I have yet to follow this to its logical conclusion. The first thing I should say is there's so much interesting stuff you can do in the area of testing and state machines that it's very easy to get intimidated and to think that it's this crazy rocket science-y domain. So the first thing that I would tell anyone who's going to try to adopt Automat and what they're going to do for testing is just write regular unit tests. If you've already got a thing that you're trying to port to Automat and it's got unit tests, you shouldn't need to change anything. Just use that as your regression test suite because it's fine. If you write a bunch of unit tests that check all of the cases that you think are interesting and make sure the behavior is correct, that works totally fine with Automat. You'll get reasonably good code coverage numbers, like everything will work more or less the same as you're used to, and you should definitely start with that, because if you try to jump straight into the deep end of model checking and generative testing, you will end up with like this explosively huge amount of stuff to learn, and it'll seem very, very intimidating. That said, the thing that you learn first about testing with Automat is that Automat will teach you that you're not testing quite as much as you thought. Like all of these systems in Twisted that I'm talking about replacing with explicit state machines that already had an implicit state machine. They already had 100% test coverage. Like we were very rigorous about that kind of stuff. And so there was no like big legacy untested code in there. It was just, now that we have a list of all of the state transitions that we can read, it's obvious that we're missing two. Like there really should be a transition from this state to this state, and there isn't one, and we just never thought to write a test for it. So why don't we just go ahead and write a test for that state transition? And that's the way that a lot of testing for projects that are initially adopting Automat will go, is you'll do all the same testing you would have done before, just plain vanilla unit test or PyTest or whatever your favorite tool is. You call the methods on the thing and they call the outputs and your logic is exercised and you feel good. And then you run Automat visualize and you look at the state machine graph and you're like, wait a second, did we cover that transition? And then you go write some more tests and you find out, your state machine maybe had a couple of bugs in it that you didn't realize before. So it's the first thing that you get out of a state machine is definitely the additional visibility into cases you might not have tested. And then you can test those the same boring old way you always have. Once you're comfortable there, then there are a lot of other opportunities that having a state machine presents. And one, this is what I said, I haven't actually done this myself, but it's been something that folks at PyCon and in the Twisted community have been talking about with some excitement, is using hypothesis, which I don't know if all of your listeners would know about that, but it's a generative testing framework for Python, sort of modeled on Haskell's Quick Check. And it can generate inputs for a program somewhat randomly, and then it can discern, based on the types of failures that it gets when it runs your tests with these different inputs, which are the interesting values, which are the ones that need to be tested. And what Automat gives you is, because now you have an explicit list of all of your state transitions and all of your inputs and all of your states, you can use that as an input to hypothesis and generate your testing data based on a kind of random selection of inputs to your state machine. And by combining the state machine and this generative testing strategy, you will rapidly find these like edge cases that may have completely eluded you, because you wouldn't have realized like, oh, these are my inputs and these are my outputs and here's what I have to test. The few cases I've seen of people doing that, you wouldn't actually be able to tell that that's what they were doing, because inputs in Automat do actually potentially require parameters, for example. And the types of those parameters still need to be in some defined range, and those defined ranges have to be specified to hypothesis using its usual test generation APIs. So it actually just looks the same as if you had applied hypothesis to your existing application code with no use of a state machine at all. But the data that was created as part of turning it into a state machine is a super useful input and thinking tool when it comes to doing the input generation step. So there's also some potentially interesting stuff beyond that gets into the realm of model checking, but I am the wrong person to interview for that particular area. So there are some things that are coming down the pipe in future releases of Automat, like a tracing API, so that you can get coverage information on your transitions, so that you can know not only where the lines of code covered, but all of the different orders that you can exercise them in were also covered. So that can provide more information both on the sort of test design side, which is where your state transition table is useful, and then also on the analysis side to make sure your code coverage is complete. There is no additional burden that Automat imposes on your code to make it testable or to do testing with it, but there are a bunch of additional opportunities that it creates where you can do more testing and you can be more confident that your testing is capturing all of your interesting distinctions.
And you mentioned the tracing API and your feedback API as well as planned features that you're going to be adding in the future. So I'm wondering, are there any other capabilities that you have on the roadmap that people should be keeping an eye out for?
Nothing terribly big. I think there's probably going to be some refactoring in the area of what we call collation, which is that because an Automat input can produce multiple outputs, there's a step where when the outputs start getting generated, they get converted into a return value for your input method. And I think some of the decisions that we made in the first release of Automat were kind of formally correct, but like not super helpful. Like it used to return an iterator, which meant that your outputs wouldn't always be run immediately, which was not really that helpful. And even now, I believe it still returns a list. And quite often what you want, if you have an input that produces a single output via its one transition, you just want to return that value. So there's probably going to be some tweaks in the way that you define state transitions to make it easier to do certain idiomatic things. But beyond that, I really think Automat it's one of those libraries that can kind of be done in that it performs a fairly simple function. One of the most important things about it is that it restricts the scope of that function, that any kind of scope creep into like, oh, let's add an automatic, hook that gets called every time you enter this state, or let's add a way to get the state out because that would be useful for debugging. Those kinds of things are explicit non-features. So I think it'll remain a fairly small and tidy library that just does this one thing. So in addition to those small cleanups, longer term, probably most of the energy will go into making the visualizations better, making it easier to extract information from the running state machine, do logging or tracing or things like that. We already have certain APIs that do things like allow you to serialize the current state that were fairly carefully designed to... Well, I guess I should explain first. I've talked a lot about how you don't want to expose the internal state of your state machine, except you totally need to, because sometimes you have a state machine like in your order processing example. The actual state transitions in that order processing example probably happen one at a time, where something happens, your state machine gets saved to a database, and then a couple of hours later another thing happens, it gets deserialized from that database, You run the input and then you put it back in the database. And in order to put it into the database, you need to know its internal state. So we tried very hard to come up with an API where you can technically get the internal state out of the state machine via a public API. That's totally doable. But the shape of that public API is extremely focused on making it really easy if what you're doing is like doing the kinds of things one would need to do to serialize the state machine to a database, and incredibly inconvenient and painful if what you want is like a .state attribute that you can check before doing something. So in that same way, we need to do some thinking about how to make sure the tracing API and the other internal things that will make it easier to get bits of information out don't accidentally make it too easy to subvert the intended design of Automat.
So are there any interesting use cases that you've seen of people leveraging Automat outside of Twisted?
It's pretty early for the library, I think. It didn't see a lot of promotion until fairly recently. As I believe I mentioned at the beginning of the project's life, Ashwini Arganti was asking about how she might use a state machine library to write a TLS implementation, and at this last PyCon, she gave a talk about, among other things, Automat, generally using state machines to design secure software. So that has sparked a lot of interest, and we're starting to see a lot of really interesting kind of proposed uses, but I haven't heard a lot from users who have done a lot kind of in anger in production yet, outside of Twisted and a couple of related applications. There were some very cool things that I heard about at PyCon, which I'm never quite sure how kind of like public these things are, so I probably shouldn't repeat any of them here, but I hope that the next time we talk about this, there'll be some really cool stuff.
So are there any other topics or questions that you think we should talk about before we start to close out the show?
Well, I guess I should just kind of give an impassioned plea to anyone who's got one of these libraries or applications that are stuck in this quagmire of way too many little state flags and way too many little values and counters that are proliferating thousands of little conditionals. Give Automat a try, and definitely like report bugs and help out on the project, because it's kind of an easy project to work on. There's a tiny public API. There's not a whole lot to mess up. There's 100% test coverage on everything. It's all in memory. It's just a data structure. So, if you've been thinking, deterministic finite-state automata, it sounds like too fancy. I'm not really a computer sciencey person. Like, don't worry, neither am I. And it can give you a lot of advantages to reduce the complexity of your code and give you more confidence that you understand what it's doing.
All right. Well, I will have you add your preferred contact information to the show, so anybody who wants to follow up and give feedback on their work with Automat can get in touch and see the progress being made on that and on its usage within Twisted. And so with that, I'll move us to the picks. And for my pick today, I'm going to choose a set of lights that I found a little while ago at Home Depot that's actually 3 little LED pucks with a remote, and it's actually a multicolored LED light, so you can actually change the hue from white all the way through to red, and you can do it either automatically or jump straight to the color, or you can actually manually increment through each of the different shades as you go, and you can also vary the light intensity. So it's pretty nice for being able to add some interesting light effects to whatever room you're in, and it's fairly affordable, so thought it was pretty interesting and worth checking out. So I'll add a link to that in the show notes. And with that, I will pass it to you. Do you have any picks for us today, Glyph?
Sure. I guess my pick for today would be OmniFocus, which is a task tracking application for the Mac and iOS and watchOS. And it's difficult to overstate my reliance on OmniFocus. It kind of runs my entire life. And it's germane to today's show because when a state transitioning event occurs in my life, OmniFocus is the place that it goes to. It's a getting things done based system that allows you to input all the things that you want to do, and then at a particular time, you can view the tasks which are sort of currently available, like things that you could do right now, things that aren't like dependent on anything else, things that are not deferred into the future, things that have an active context. So like you can have different contexts for home and work and different people that you might need help from in order to do a particular task, and you can activate and deactivate them and then see a view of just the things that you kind of should actually be doing right now. Big fan, always glad to promote the excellent work of the Omni Group, which is the software company that makes that app.
All right. Well, I appreciate you taking the time out of your day to talk about Automat and the work you've been doing with that. Definitely seems like a very interesting and useful library. So I appreciate your time, and I hope you enjoy the rest of your evening.
Thank you very much, and thank you for the opportunity to spread the gospel of state machines and not having a million if checks.